The first ever mathematics lecture is being hosted here on twitch.tv/Neuro. I am joined by guest Brett, who is coming at us with an intro to mathematics discussion, November the 16th, 2019. What is up, Brett?
Hello, Neuro. Thank you for having me.
Yeah, it's my pleasure. So, I guess we kind of started off the venture to do this with just some random comment that I was making while playing StarCraft about the beauty and joy of mathematics and how a lot of people don't really ever get an opportunity to focus on not just the math you have to do to get through the class, to get to the next grade, but why math is fun and engaging and awesome. And that's partially the mixed bag of different quality of teachers that you get and that sort of thing, but there's a lot of excitement and beauty and challenge in math. And as a StarCraft streamer, my community is very interested in that kind of strategic depth. Math is a space that has a lot of skill that you can show. There's a lot of room for creativity, a lot of reward for precision and finding elegant solutions to the problems that you have and things like that. So I feel like mathematics is one of those domains that gets a bad rap because you do have a lot of boring math teachers who are just kind of like a squared plus b squared equals c squared, and they don't really light that fire in the student's mind of this is a really amazing subject that has a lot of utility and versatility if you know how to apply it in those ways.
Yeah, I think that's very well put. It's almost like there's this secret world of math that we only save for the math majors. There's like the classes that I guess engineers and other people take, like maybe your experience with math is you might have taken a calculus class and you find that it's just like a sequence of like, apply this formula I told you to this other problem, like see how many formulas you can remember, like use this cookbook of techniques to solve these problems. And it isn't until you pass that introductory math and get to the later classes that math majors take where you actually, it's almost more like a philosophical or logical argument where like a lawyer, you're trying to defend and create different mathematical theories. And each one requires logical arguments that follow from the one before it. So you really develop this mathematical way of thinking. And you don't often see that at all in those early level classes. That it's only when you start taking the classes that math majors take that some of that beauty comes out.
Yeah, for me it was the fundamental theorems of calculus course, which is also called analysis in some circles, and that's when you really get into writing proofs and focusing on the basic building blocks of math. And I was actually kind of annoyed when I took that class because to me it seemed like we should be starting with this because this is the basic structure of how math is built up. Math is a built structure. It's made by people to describe reality. It's kind of like a scaffolding. That's the way I think of it. It's a scaffolding for reality where it's not precisely equal to the way that the world is and the universe is. That's why applied mathematics is a lot more messy than theoretical mathematics, but it's amazing in how broad and vast it is, and it's really exciting to see the different discoveries that mathematicians have made over the course of history that built key parts of that scaffolding. Like Isaac Newton is one example where he's sick over the summer and he invents calculus, which ends up being a super useful branch of mathematics for us moving forward. And if he didn't do that, then someone else would have had to. And it's a really beautiful and engaging process. But yeah, most of the early math classes that people take are purely mechanical and procedural. It's like you learn the symbols, you plug in the stuff, and then you find the answer. And that's the whole extent of math. It doesn't really teach people to think mathematically in a creative way for themselves.
Yeah, I mean, yeah, that's very well put. I mean, even in the discussion we do today, because we're going to have a little bit of a period where we talk about the history of one branch of mathematics, probability. Originally, people were just doing calculations because they had some problems that they wanted to solve. And then it wasn't until actually the beginning of the 20th century that they actually came up with that formality you were talking about, an actual rigorous, coherent theory to describe the probability. And that's the one we use today. But yeah, but to see the development of it and to see why people made different discoveries and how something develops is going to be hopefully interesting for everyone. But I also just agree with your sentiment. I mean, there's so much interesting parts of math that I guess sometimes people don't see in their classes. And once you learn the math, the way it's sort of the language of science and economics and engineering, and to see how it's able to, how it's been so successfully applied to these fields is quite amazing.
Hell yeah. Let's dive into it. What do we got?
So maybe one more thing about this, about math in general. There's, it's funny sometimes when you look at for those who have taken or looked at math classes in a university setting, some classes have no prerequisites that seem like they should be very difficult, and the only prerequisite they have is something called mathematical maturity. And I think that's kind of like one of the things we're trying to bestow upon the audience through this sequence of podcasts. This notion of the way mathematicians think about a problem, a very precise, almost pedantic, lawyer-like way of looking at statements and constantly asking why, what is the definition of that, and making sure like all of the arguments are airtight. And I think if we could get to that point where sort of we've created an audience full of pedantic mathematicians, that'll be a very interesting, I guess, achievement.
Well, the real take-home value, and this is the tough thing for a lot of people when they get into a mathematics course and they see a certain kind of problem and their immediate reaction is, I'm never going to use this in my job. There's like all the different careers that they could go into, and this problem that they're faced with right now isn't going to apply to a single one of them. And some people will say, well, then it's not worth it for me to even do this, when mathematical maturity is more of a sense of rigor in the way that you think in general. It's not just how you perform a particular type of problem. It's even when you're debating stuff with people, it could even be politics. If you're establishing a chain of logic, you should be able to understand what a solid premise is, how to establish that solid premise that's agreed upon between you and the other person, and then to prove your point from one step to the other where every link in that chain is really solid. That is something that involves mathematical awareness. You don't always think about the numbers and things like that, but a lot of people, they half-ass the way that they just talk to other people in conversation and the way that they carry themselves in discussion and debate. And training your mathematical mind and your mathematical maturity has a lot of benefits in that sense.
Absolutely. And I think I know you have many gamers in your audience, and I think for gamers in particular, there'll be a lot of things that we work on, hopefully in the podcast, that might be interesting for them. I mean, in some ways, learning math and working on math puzzles is kind of like making various achievements in a game. But not only that, there are certainly mathematical ideas that come up in a lot of the games people play on Twitch. There's certainly, whenever people have, I guess, RNG as they call it, when they're encountering some randomness, maybe they're playing a card game, or maybe it's the percentage of a given drop in WoW, and understanding what decisions they make, there could be some ways to mathematically model this that would improve the outcomes in the game. So I think that could be interesting, but also in terms of like collecting data, if you want to do some kind of data science application, or you want to better understand machine learning and all the crazy stuff you hear on the internet about computers taking over the world, math will definitely give you access to that material.
You heard it here, folks. If you want to increase your power level IRL, do math.
Exactly. Without further ado, shall we start?
Let's do it.
All right.
Section 2, Brief History of Probability Theory.
So I guess we should start the brief history with a disclaimer, which is that I am not a historian. And there's a huge world of history of mathematics that you can learn, and many places online to look for it. But my expertise is in being a mathematician, and the math I do is analysis, probability, some of its applications to data science, but not specifically on the history of math. So I'm going to try to do my best to present some of the topics in this history, but there's going to be plenty of omissions. And if you have any extra information, or you see maybe a mistake in something I present, please present it, because I'd be interested to know.
Sweet. Sounds a little bit like the Agent Smith disclaimer. I'm not an expert in everything I talk about. But you're the figure of authority right now, therefore you must be correct in everything, right?
Actually, that's correct. I am correct in everything. Although, like, amazingly, some of the people we discuss we're experts in so many things. It's like, I don't even understand. Some of these historical figures that basically invented everything. Also, another disclaimer, I may butcher some names. We'll see.
Okay. Sometimes I can help with those. We'll see.
I'll be impressed. Well, anyways, so where did it all begin? And as far as I know, some of the earliest basically looks at probability theory didn't really come in the form of chance, but they came in the form of analyzing frequencies of letters in different words in Arabic. And there were some mathematicians slash philosophers, because back then people did lots of different things in ancient Iraq that were looking at like the letter frequencies in different words of Arabic. So the image you see here is of Al-Khalil, who first studied different ways of counting the letter arrangements in Arabic words. And in the next image, Al-Kindi used these word frequencies to develop the first cryptographic algorithms. So what they would do is you would get some kind of encoded text and you don't know how to decrypt it, but you know which letters occur more frequently than others in Arabic words. And to use that, you can develop heuristics to better decipher the cryptographic text. And this was like the first work on cryptography ever in the Islamic Golden Age. And you could think of these word frequencies, letter frequencies, as like a preliminary attempt to look at the chance of something happening. And this, I think, is maybe, again, not an expert on history, one of the first recorded, I guess, attempts to look at probabilities.
Cool.
Now, later in the European Middle Ages, this roughly 1,000-year period, so it's pretty broad, it seems that odds and something like probabilities were also used for things like insurance, for insuring different endeavors, and for betting on simple games. But the calculations were very intuitive, like, oh, that'll be 10 to 1 or something. So they weren't really based on a calculation. There wasn't this theory of formulas and calculations that we would call like a rigorous mathematical theory. And it wasn't until it seems about 1564 when the Italian mathematician Cardano was looking at problems in terms of counting the outcomes of dice. So, for example, he was looking at the number of ways to get a given sum when 3 six-sided dice are thrown. And he wrote a book on this entitled The Book on Games of Chance, which contains the first systematic treatment of probability, where you consider ratios of the favorable outcomes you're looking for, like maybe getting a sum of 7, to the total possible outcomes. And you can even get English translations of this book. I think there's one, and along with commentary by this Norwegian mathematician Ura, and you can find that on Amazon if you just look for like the book on games of chance. So later, there's a French writer and amateur mathematician. His name is Antoine Gombeau, also called Chevalier de Marais. And he was attending something called a salon. So at that time, there were these gatherings and get-togethers where people would join and like discuss varying topics that were interesting at the time. And at this one salon, he proposed to two mathematicians there the following 2 questions. And I think on the next slide, you see the first of these 2 questions, which is, there was a game people were playing, and he thought it was unclear what the right answer was, which is, which of these 2 scenarios is more likely? And it's just involving simple, fair, 6-sided dice. The first outcome is, what is the probability, well, which of these is more likely, really? At least 1 6 in 4 rolls of a fair 6-sided die, or getting at least 1 double 6 in 24 rolls of a pair of 6-sided die? And knowing the outcome would help you know which way to bet if you were playing such a game. There was also a second question, which I don't have a slide for, which is the so-called problem of points, which is if 2 people are playing a game, and let's say they're playing a game with even odds, and it has several rounds, like maybe you're playing like a best of 7 or a best of 11 with somebody, but the game has to stop prematurely. How do you split the prize at that point? You want to take the total pot and split it amongst the players, but how do you split it? And having heard these two questions, two mathematicians, which we have images for, Blaise Pascal and Pierre de Fermat, worked on these problems over a series of letters where they corresponded. And in those letters, they basically created the modern theory of probability, including detailed calculations. For example, using if some people have heard of it before, Pascal's triangle, and the notion of what expected value, or EV, is.
Ooh, that's used a lot in poker.
Yeah. So the beginnings of these theories in poker came from the letters between Pascal and Pierre de Fermat. And it was initiated by this question from Antoine Gombeau. So later, one of the people who's corresponded with Pascal, Christian Huygens, a Dutch physicist, wrote a book on gambling called On Reasoning in Games of Chance, where he collected many existent results on probability and wrote some of his own. And I think for all these people, you'll have pictures. There was also the Swiss mathematician, Jacob Bernoulli, who is attributed with the first writing of the law of large numbers, which is a very important result, one of the most important results in all of probability. What that says is, if you take a coin, maybe it's weighted, it has some probability of getting heads, and you flip it many, many times, and you say what percentage, what fraction of the flips is heads, that will, as you flip more and more and more, give you a better and better approximation to the true chance that it will give you heads. And this is the first time such a law was really put down in a formal way. And that's a very fundamental result. I mean, it's not only fundamental in probability theory, I mean, it's how we think about probabilities is some way really connected to the law of large numbers. It's also connected to why statistics is possible. That by taking averages of lots of data, we can then learn something that's sort of true.
So one little anecdotal thing that I've noticed here that connects with a lot of what Agent Smith and I have talked about is the different time periods where people were either more in favor of intellectual discourse and discussion or kind of opposed to it and more focused on the strength of your convictions. So from the slides that you've collected so far, just from this set, we had the Islamic Golden Age and some slides there and some progress that was made where it was very much in fashion to be thinking about new ideas and pushing the boundaries of science and things like that. And then here we've got in the Renaissance where it is very much in fashion and style to meet at a place and then talk about some probability and stuff. Like, you don't really think of walking into a Starbucks and, oh, there's a probability discussion right now. So it's cool when you find interactions like that where people are trying to learn and have productive conversation. Pretty refreshing. It would be kind of interesting to imagine walking in on one of these.
Yeah, it was interesting reading about these salons where like someone would say, okay, this is a discussion on like the politics of the time or maybe contemporary art. And I want everyone to like give their feelings, and maybe you'll have some experts there that are helping guide the discussion. So yeah, it was a very interesting time. I mean, I guess you sometimes get discussions like this in certain academic settings, or maybe on podcasts like this. Maybe this is the modern salon.
Mm-hmm.
After Jacob Bernoulli, or maybe contemporary with Jacob Bernoulli, there's also the French mathematician Abraham de Moivre, who wrote the first probability textbook called The Doctrine of Chances. And he also gave a formula called the central limit theorem, which is also central to probability and one of the most important results. And in this context, it was, if you flip a coin many, many times, what does the histogram of the sum of the number of heads look like? So suppose you flip a coin 30 times, you'll get some number of heads, and then you'd repeat that. You flip it another 30 times and you get some number of heads, and you flip it another 30 times and get some number of heads, and do it a bunch of times and make a histogram of those results. That will look like a bell curve. So, or in mathematical terminology, we call it a normal or Gaussian distribution, and that many things follow this normal Gaussian distribution is one of the most important results in probability and is also very important in statistics. Mm-hmm. So these two results, the law of large numbers and central limit theorem, are really some of the pinnacles of the theory. And this was one of the first times it was mentioned in this book, The Doctrine of Chances. So I think you have an, yeah, okay. The next, so the next contribution I'll discuss came from Carl Friedrich Gauss, who made so many contributions to so many fields. It's sort of incredible. Gauss sort of did everything.
That's where Gaussian
One
distribution comes from.
Yeah, Gauss. His name is attributed to that, but like the physics, the math, the inventions, everything. I mean, he's one of these people that it's unfathomable how much he did. You could have like a whole series of podcasts on just what did Gauss do. So one thing he did for probability is in taking scientific measurements and analyzing the errors, he applied probability and developed a theory called the method of least squares for analyzing the measurements and the errors and trying to fit some type of model to it. And more work was done on least squares and the associated method called linear regression by the French mathematician Pierre-Simon Laplace, who also extended and generalized de Moivre's work on the central limit theorem. So he made many important contributions. And so at that point, we're getting to the beginning. Well, I should also add that I've left out lots of probability. This is by no means a comprehensive list, but I want to get to a different part of the history now. And I'm sure for those interested, you can find lots of resources online about all other aspects of the history of probability. But something that we discussed earlier in the introduction is that even as late as the 20th century, there was still uncertainty regarding the formalization of probability theory. Despite years of success applying the theory to various problems, computing things for gambling and science, insurance, probability still lacked an agreed upon formal grounding. The people working in probability would say things like, this is an event, or these are independent trials with certain outcomes, or this is random. So they use these sort of like words and quotes, but those concepts themselves had no mathematical meaning. And it was partially an issue that was coming up because the probability theory was being used more and more in physics, and they wanted a more complete model for describing these physical phenomena. So they wanted more formality from the mathematics. In fact, that next image you were looking at is the mathematician David Hilbert. And in the year 1900, the German mathematician David Hilbert published a list of what he said were in his view, the 23 open problems that were most important. And these became very influential in 20th century mathematics. Some of those problems are even still unsolved today. One of them was the Riemann hypothesis, which is a famous mathematics problem that there's $1 million prize for. He presented 10 of those at the Paris conference of the International Congress of Mathematics, whereas a meeting where lots of mathematicians of the time meet, and they still meet to this day every 4 years. And I think the next picture has an image of where they met in 1900. And part of Hilbert's sixth problem asks for an axiomatization of the theory of probability, in particular to formalize the techniques used when probability is applied to physics and statistical physics. And I think so if you look at after the slide with David Hilbert, there's a picture of the Sorbonne amphitheater where I believe they met. And there's also a transcript of David Hilbert's talk at the ICM.
The future problems of mathematics.
Indeed.
That's pretty cool. So, it's like the high council of math. It's like, guys, these ones are really hard. Can you help?
Yeah. What's also amazing is that he had such vision to really come up with problems that captured all mathematicians. And it became a big program to solve those problems. He's like, yeah, everyone hold up. This is what's important. Let's work on these. And that really, really captured everyone and became like important for many years to come. Mm-hmm. Maybe an interesting aside on one that doesn't have anything much to do with probability, but has a very interesting answer, a sort of philosophical answer. So the 10th problem was to determine an algorithm for solving these things called Diophantine equations. These are certain equations involving algebra and integers. So the equations themselves, we won't discuss much here. But the surprising answer, which I don't think anyone thought at the time, was that these problems, coming up with a general way to solve these problems, is actually impossible. So it's weird. Usually I think they would expect, oh, this is just going to be hard. It might take us a long time to figure it out. They didn't actually expect the answer, no, that's impossible. You'll never be able to do that. And to actually solve that problem required the formal theory of computation, which was later developed by people like Alonzo Church, Alan Turing, Kurt Gödel in the 1930s. And so Hilbert was asking for an algorithm for solving this problem. And if someone presented an algorithm, you could look at it and say, oh, that looks like a method. I can follow that. But it's a much harder statement to say no algorithm exists.
Yeah.
And even thinking about what would you need to do to say you could never make an algorithm ever to solve this problem is a very difficult question. And that's why you needed to build a formal theory of what an algorithm is to actually answer no to a question which it seemed impossible. It seemed like unfathomable that the answer could ever be no. And that was later done in the 1970s, building on this theory from Church and Turing and Gödel. And that's an interesting topic we could look at. I mean, there's lots of interesting topics that we've kind of spent only a few minutes on in this history that we could definitely focus on in later podcasts if people are interested. Like we could try to solve Gombo's questions together, or think about what it means for there to exist no algorithm, so that maybe this problem will never be solved because it's unsolvable, provably. But let's return to probability, as you just were with the shifting slide. So we have this outstanding question. David Hilbert, 1900s, like, one of my problems, the 10th problem, is probability is still in a state where it's not formalized. And we need formalized techniques to help with our development of statistical physics. Let's try to make progress on this. And in 1931, the Russian mathematician Andrei Kolmogorov published an article which led to the axiomatization of probability that we use today. The key idea was to define probability in terms of measure theory, and I'll say what that is. So measure theory, developed by the French mathematicians Henri Lebesgue and Émile Borel, which you, I think, have slides for, is the modern theory of area and volume, and also, for those in the audience who know, integration from calculus. And it was the connection and the building of probability theory on top of measure theory that really was the formalization that everyone was looking for. And it's stayed till today. Kolmogorov's axioms are the ones we use in modern probability. And Lebesgue and Borel's measure theory is what we use in modern analysis. And so to better understand this connection between probability and area, I want to look at a simple problem. So let's consider a square that is 2 by 2. And I want to throw darts at this 2 by 2 square in such a way that any point on the square is equally likely. So you can imagine just a process where we throw darts and we could hit anywhere in the square with equal chance. Now suppose that inside of the square, we draw a circle of radius 1. We want to ask the question, what is the chance that our dart will hit the circle? So in terms of area, the area of this circle, I'll just tell you, I mean, using this formula, if someone remembers it from school, pi r squared. Since the circle's area has radius 1, the area of the circle is the number pi. And the area of the square is 4. So the ratio of the circle to the square is pi over 4, which is a little more than 3/4, about 0.75 chance of hitting the circle. So this is a way in which, like, the probability of this event, like throwing darts, can be connected to something like area. And measuring the area of something is closely tied to measuring the chance of something. But I want to do a little experiment that we can take this even further. And this is something that could be repeated by anyone who can program. It'll be a short program you could write in whatever language you're comfortable with, where we're going to simulate throwing thousands of darts at the square and counting what proportion of them hit the circle. And I did this with I think I wrote this one in Python maybe, and just used RNGs from Python, a random number generator, to generate the dart throws. So after 5 dart throws, you'll see it on the next slide, some fraction of them hit the circle, some fraction of them don't hit the circle. And you take the ratio of the ones that hit the circle within the circle to the ones that do not, I mean, the total number, and you can get an estimate for what you think the area of the circle is. And only with 5, you see it's not a great estimate. But we can keep throwing more and more darts. So you can throw 10, 15, 25, 50. And as the number of darts increase, we're getting a somewhat more accurate approximation. And we can go all the way up to 10,000 darts. Each time tracking the number of the darts that lie in the circle to the total number of darts thrown, where the red crosses indicate darts that hit the circle, and the blue crosses indicate darts that miss the circle.
Nice. Yeah, this is one of the connected to one of the phrases that has stuck with me a lot, mainly from poker. But you could say that as the number of hands you play reach infinity, you get closer to the actual representation of what the odds are. On any given day, you could have good luck or bad luck. You could be rewarded for a good play, or you could lose money playing perfectly. But if you continue to play more and more hands, then it's going to get more and more close to the correct representation of your skill level and your value. So the question is, how much volume can we get? So in this case, it's as the number of dart throws increases, it gets closer and closer to pi over 4.
Indeed. And understanding this process at which the numbers get closer and closer to the true value is done using things like the law of large numbers and the central limit theorem. So those theorems that go all the way back to the 1800s are really critical in understanding these phenomena and understanding your poker games. Mm-hmm. This method we looked at here is called Monte Carlo, named after the city in Monaco known for gambling. And it was first used by the Italian physicist Enrico Fermi, but never published any results on it. The theory was further developed in a major way in the late 1940s by the Polish nuclear physicist Stanislaw Ulam. Both Fermi and Enrico Fermi and Stanislaw Ulam worked at the Manhattan Project. And the Monte Carlo methods are useful in simulations that are needed for making calculations in nuclear physics. And today, Monte Carlo methods are used in many fields, such as including physics, chemistry, finance, engineering, medicine, just to name a few. Now, there's many, many results in probability that have happened since the 1930s and 40s, and there's many results that we left out. But this was just kind of a feeling for some of the history of probability. And hopefully people thought it was interesting. We definitely left out some major things. There's a whole philosophical theory about how do you interpret probability? What do these mathematical models for probability mean, and how do they connect to the real world? Also, the whole field of statistics is used by probability and data science is very interesting, but maybe something we don't have time for.
One of the key things I think to lay out as a foundation here as well is that mathematics is the effort to find the true and correct answer, and many times we're starting from human intuition, which has a lot of mental shortcuts that give us an answer that works in a hunter-gatherer context more often than it fails, but it's still not really what you want to be looking for. So an example would be gambler's fallacy, is a cognitive bias where if you feel like you get a few reds, then it's like, well, I'm due for a black now. And that's something that most human beings, they feel that way about the outcome, unless they've been specifically trained to be aware of that bias and to understand the correct mathematical nature of what's in front of them. So I've noticed that a lot as well in MOBA games like Heroes of Newerth and Dota 2, where you'll have a rune that can spawn either top or bottom, and people will go for the different one because they feel like it's about due for that when it really has no impact. Unless in the game they have things like pseudo-random as opposed to random, which can be useful to familiarize yourself with. A pseudo-random thing, for example, if you have an active or a passive ability that hasn't procced for a while, sometimes the chance of that increases over and over again, which basically fits the gambler's fallacy bias, where I haven't had this for a while, so I'm due for it now. That's a pretty key thing.
Yeah, the game correcting for people's biases is
yeah.
funny, yeah. Yeah, it's a good point that probability is ripe with problems where your natural intuition gets them very wrong. And yeah, there's lots of history. In some respect, there's a lot of finance is based on the fact that people who can better spot these biases are more equipped to be successful when they're trading.
I took
I
a
think,
judgments and decision making course. It's kind of a combination between math and psychology, and it really lists off a long list of cognitive bias that we're basically wired with that causes us to make bad decisions really often. And that class was part of the reason I ended up going for poker in the first place, because with that long list of mistakes that people make consistently just because it's natural for us to think that way, I was like, wow, people play this game for money without doing their research on how it actually works. This seems too easy to be true. It turns out poker has a lot of math to it in and of itself, and it requires a lot of study. So more than I expected. And I did get my ass kicked starting out, but it was just at the penny stakes and whatnot. So it was a humbling experience in two counts. For one, taking that course and then seeing the different common mistakes that we make. And then for two, not really respecting the depth of the math of poker.
yeah, it can be very complex. I mean, also, I know you play World of Warcraft on on your channel. There's lots of probability questions that can be asked there, and I mean, a simple one, but maybe this is too simple, is if you're trying to get a particular item dropped from some enemy and it drops with a certain chance, you might think, as kind of like alluding to what you were talking about before, after you've killed the monster, let's say 20 times, that now it'll be soon that you'll get the item. But actually, the number of times you killed it doesn't really matter unless they're doing something pseudo weird like you were describing.
Yeah, so the main one that is relevant to my character, and it's one of the really exciting items from the game, is Thunder Fury, Blessed Blade of the Windseeker. And for that item, there are two separate bosses, and you need a unique drop from each of them. And each of those drops is 3% chance each. And we've not seen either of them yet. So it's going to be quite a grind.
Yeah, so if like let's say you think to see one of them, just like we talked about one of the items, you'll think, oh, maybe I'll need about 33 times killing them on average to see one of them. So after you've killed that boss 10 times and you haven't seen it, it's not like there's 23 left. You still have 33.
Yeah.
So that can be very deceiving.
Mm-hmm. Yeah, it's an interesting aspect to managing your human morale with probability, because I think luck in life is something that we can definitely feel, but you can't plan for it. You've got to just consistently do your thing and work hard. With something like streaming and content creation, you'll get maybe 2 or 3 lucky breaks a year where something goes viral and you get a big boost and things like that. But probability in life, unfortunately, really doesn't give a shit about us. I think sometimes it would be nice if there was the immediate karma of reward or punishment for doing the right thing or the wrong thing. But probability is very weird. It's very cold, and it has strange patterns that I think don't really fit what we would expect. I definitely noticed that going through the swings of poker. Of you have certain dry spells where it's just really flat. You have massive lucky winning days, and then you have some really crushing bad stuff, and then all kinds of mixtures in between. Probability is a really interesting beast.
Maybe a positive twist to that, on the other side of its coldness, is I've been fortunate in my life to know a bunch of people who were very successful stock traders, and they were quantitative traders. And the thing that sets them apart is being very objective and analytical with the way they look at things. So someone who is maybe not as savvy with the probability will, on these ups and downs, be sort of affected emotionally and make decisions based on the trends and not see the bigger picture. But by training people and by learning probability, and maybe that's one of the things we could spend more time on in these podcasts, so you can train your wit to be more knowledgeable about the forest instead of the trees, and over the long run, improve your performance in whatever you're doing.
Mm-hmm. Yep, that sounds a little bit like tilt management, when the emotions impact your decision making in the negative and you start making bad moves because you're upset.
Yeah, like one day you lose some money and then you decide, oh, there's no way I'm ever trading this product again, or this strategy is terrible. But like, if you just compute the probability that this would happen, it might be totally within the realm of normal possibility in a very good trading model that you'll lose some amount of money each day.
Hmm. Yeah, there is that realm of bad luck. Like you just got a bad beat. I remember one of my poker hands that I played. I had basically every single other card that drops on the river, I win the hand, but they ended up connecting with their quads on the river when they had to make a mistake every street leading up to the river to be able to make it there. So they played the hand in the most terrible way they physically could with what I had. I think I had some amazing hand, but I had anything but that one card and I would have won, and I lost my whole stack from it. But on my Hold'em manager, it showed my expected value go way up. So that was like the one little silver lining, was I could see that that line that I took is going to make me money almost all the time, and this was that one little bit of bad luck. It still hurts, but it is one of those situations where you can play perfectly in poker and you could have a good strategy in trading, but it's not necessarily going to win this time right now.
Absolutely. Yeah, it's a great example. So this might be a good time for the Q&A section where we could ask various questions to the audience or talk about some things we want to do in the future. Up to you.
We did have one question from Drake about Gödel's incompleteness, which I believe was the 10th problem.
It's related to the 10th problem. Is this Drake the rapper?
Maybe. Drake, are you the rapper? I think he was just asking about if that was brought up at this epic mathematics council meeting.
So Gödel's incompleteness theorem is closely tied to the resolution of the 10th problem. So this notion of something being uncomputable, or there can never be an algorithm to solve this problem, you can make a pretty close connection between that and incompleteness theorem. And those kinds of topics, I think, might be something very interesting. It's like a math/philosophy podcast if you want to do something like that in the future, where, I mean, even the concept of there being problems that are sort of unsolvable by humanity in a provable way. The humanity may be a little bit of a headline. I mean, you have to make precise what I mean by that, but that whole notion is actually quite interesting.
Mm-hmm. Yeah, Gödel's work is one of the main points in Gödel-Escher-Bach, as the name suggests, which actually I need to finish that. I'm about 3/4 through it. It's one of those books that's like taking a course as you go through it. Have you read it by chance?
I have not, but I've heard many good things about it.
Yeah, it's very interesting. It addresses a lot of stuff. It doesn't really solve everything, which I think for some readers isn't the most satisfying read. It's not like he's breezing through stuff, connecting all the dots and telling you like it is. We do have some people who, it's sort of like a snake oil salesman process where they claim to have unified great things. Athene in the gaming scene, he is kind of notorious for making a series of videos and claims that he unified quantum physics and mechanics and all these other things, which is very silly. It's fun and it's exciting if you tell people that you've figured everything out, but oftentimes describing the landscape is as far as you can really get. So if you're trying to connect things, as he does in Gödel-Escher-Bach, between mathematics and consciousness, you're not really going to finish the problem because we don't have a theory of consciousness yet. When you were talking about this progress in understanding probability theory and making axioms for it, that's a really, really long and difficult process. And the process of doing that for consciousness of the human brain is still in the very early term. We're trying to figure out, how does the mind work? How can we figure out how neurons form new connections by the process of neuroplasticity? We have no idea. So if someone tells you, they're making shit up.
Absolutely. I mean, my expertise more on the math side, trying to compute odds of things has been around for many, many years. We saw just a glimpse of the history of it going back hundreds of years. And not until 1930 was there really this formalization, which is fairly recent. So yeah, it totally agrees with what you're saying. It's not easy.
Cobra X asked a good question. So he's confused about the probability thing. Isn't approaching infinity kind of a guarantee that statistics will go our way eventually? If I want Wind Fury at around 33 kills, isn't it fair to say that we're closer to infinity than we were when we started, thus closer to probability hitting for us? If I can take an initial stab at this, because infinity is a really fun topic that I don't think I ever tackled too much until that Fundamental Theorems of Calculus course. Infinity is large. Not just large, it's infinitely large. So 33 toward infinity is basically no progress. I would think of it as no progress from my human intuitive sense. It is progress, but not enough that it's really going to impact much at all.
Yeah. So your hot take is infinity is big.
Infinity it's bigger than you think it is. You can't even describe it. You'll get dizzy and you'll fall over.
So I guess the comparison would be, maybe this may be what Cobra X is asking, but suppose you played the lottery like 33 times. Do you think your 34th time you're more likely to win than now that you've lost 33 times? And that doesn't change. It actually doesn't change it at all. You're playing the same lottery with the same chances. But before you play the lottery at all, if you're like, am I more likely to win if I play 34 times than if I play, like right now, before I play any of the times, what's my chance of winning? And or maybe if I play 1,000 times, is the proportion of times I'm going to win going to be closer to the true probability of winning the lottery? That is true. So you can say that before you start, say, I'm going to embark on this very painstaking adventure where I'm going to try to kill this boss 1,000 times, and it has a 3% drop rate. Do I expect to get about 30 drops? Then you can say that. But having killed them 33 times and not gotten anything, you're basically at square one. You get nothing from that. The next time you kill it, it's like you killed it 0 times.
Yeah, there was correct me if I'm wrong, 1 divided by infinity is equal to 0, right?
So I can give you 2 answers there. So one is in the right context. So yeah, so part of what we're going to be talking about on these podcasts is being precise and thinking, with a great deal of precision and being sort of pedantic. So one way of saying it is division is defined by taking one number and dividing by another non-zero number. And in many contexts, infinity is not a number. So you would just say, can't do it. Sometimes it's convenient to make infinity a number. And in those contexts, 1 divided by infinity can be interpreted as 0. And that is something that sometimes comes up in parts of analysis, to allow yourselves to actually divide by infinity. And something like that can happen. There's also this thing you learn in calculus about these sort of indefinite forms that occur when you're taking limits. So if like you have 1 on top and the bottom is tending toward infinity, that limit's going to 0. So that's another time when some people talk about 1 over infinity, when they're not literally dividing by infinity, but they're dividing by something that's getting big.
Yeah, so what you're saying is I can be correct if I really want to be, but it's not really that correct.
Well, yeah, so for example, if someone's in a calculus class on a quiz, like a teacher could say, if you wrote 1 over infinity equals 0, they could be like, you shouldn't be dividing a number by something that's just like a symbol that looks like an 8 on its side. You only divide numbers by numbers.
Oops.
But the whole notion of infinity is actually a very interesting topic, and like one that could also be another topic for a great podcast where we talk about how calculus and Newton and others, the theory of infinity, and also like Cantor and the notion of infinite sets, this whole notion of how mathematics has come to grasp with infinity, and how questions of infinity plagued the philosophers of old, and they had all sorts of puzzles and paradoxes about, but because there's infinity here, this will, like, there's something wrong with the world, and how we came to grips with infinity. It's very interesting.
What's wrong with that man? He's been bedridden for 4 days. What happened to him? Oh, he's trying to think about infinity. Oh, is there a cure? No, he's still thinking about it.
This is not a joke. There have been mathematicians who have definitely had some trauma, psychological trauma, from trying to work with the infinities and trying to puzzle them out. Now, I believe this is true, but maybe I can come back and revisit this topic. So who knows? I might be proving myself wrong later. Cantor, initially, when he proposed his theory of infinite sets, a lot of mathematicians didn't like what they were hearing, and they're like, no, 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 this can't be right. And both the negative responses he was getting and the inherent difficulty in the problem definitely caused a bunch of psychological trauma to Cantor. So it's true. Infinity can definitely keep someone in their room or in bed for a while.
Yeah. Math is very humbling for sure.
I think I'm also getting this problem right, where it was Zeno who was saying, so you want to run the entirety of a race, and you first have to run half the race, and there's half left. But then you have to run half of what remains, and then there's a quarter left. And you have to keep on running half of what remains. There's so many halves, infinitely many of them. How will you ever finish the race?
That guy would be a terrible runner, let me tell you.
And it is true, Zeno just never finished the race. He was a terrible runner. No. So that problem is one of the ones that calculus actually provides a very interesting answer to.
So the Cobra X is still asking about the when Fury drops. So we talked about gambler's fallacy before, where the previous instances don't impact the current setting. So if the chance to get the binding is 1 in 33, we ran it last week and it didn't drop. This time when we run it, it's still 1 in 33 chance to drop every single time. Even if we've killed that boss 50 times, it stays 1 over 33. It's like the boss doesn't care how many times we've killed him. I had to do that for Herod. I had to kill the guy 17 times. It's a pretty low drop rate, and he didn't care that I had killed him 12 other times. The 13th time, he still didn't drop it.
Yeah, sometimes what's interesting about this is I think we have this internal intuition for how some of these things work. And sometimes if you phrase the problem in different ways, it changes the way we think about it. So for example, you can say, okay, I need to kill this boss to get this drop. It's like 1 out of 33. What's my chance? And they say, oh, it's obviously 1 out of 33. Come on, that's how the game works. And you're like, oh, I didn't tell you that I already tried 20 times and I didn't kill it. They're like, should they change their answer? Like, should you have known? Or should, like, how many times they killed it? Like, should you, like, try to purchase someone's WoW account who's already, like, not gotten an item many, many times? So you're like, now I'm gonna get it on their account, because they built up all these non-item drops.
Don't get it. It's a cursed account. That's why it didn't drop. That they have a curse.
Yeah.
We do a lot of these different associations, I think, to give us hope. Co-Brexit, that's really depressing. A lot of it, yeah, it's, I was saying it's cold, but if you understand how it works, then that can also help your expectations as well. So basically when I'm going into that situation, if it drops, it'll be a huge hype train. People will be screaming in voice comms, and it's going to be a good time. If it doesn't drop, we've still downed some content together as a team, and our overall team strength is increasing. So it's one of those situations where you try to find the positive. Maybe you gain some experience. You didn't get what you wanted that time, but it could have been a valuable expenditure of time. I would contrast that with purchasing a lottery ticket, because you've got certain moves that you can make that have a small chance of success. Some of those might be a good move because it's a good bet for the times that it works. For something like a lottery ticket, if you do win, it's a ton of money. Also some other problems that come with that. But it loses so much more often than it wins that it is effectively a stupid move to purchase a lottery ticket for financial gain. The only good move for purchasing a lottery ticket is if the cost of the ticket is worth the fun and the excitement that you get from purchasing it.
Yes, definitely. I mean, another thing that the lottery ticket plays on is this notion of being able to perceive large numbers. So to some extent, being able to appreciate how low a chance it is of winning a lottery and how much money you're making, these sort of usages of these huge numbers really play with our intuition and test us. It's very hard to know what the real chance is. You need some kind of good feeling of what to compare it to, and effectively, I think it really screws with our mind.
Yeah, there's also, as part of the mathematical maturity concept, the practice of trying to accept something that doesn't necessarily fit your intuition in a way that it clicks and you're like, ah, yeah, I got it. I got it now. Sometimes you understand what happens. I think quantum physics is one of the ones that's notorious for this. If you understand how it works, it doesn't sit well with you because it betrays a lot of how human intuition works, where we have stuff like object permanence, where things are popping into and out of existence. It doesn't feel right, and it doesn't necessarily have to feel right for it to be correct, because this is the pursuit of truth, not the pursuit of something that feels nice to organize and write out.
Absolutely. I mean, you can imagine that we're some this. If, well, I guess one way of looking, one perspective is like if we're this AI that has been trained on survival and hunter gathering, why should this complex theory of how small particles interact make sense to us? Why should we have developed that through evolution? There's many things that could be true that don't have to feel good to us.
Mm-hmm.
Yeah.
Yeah, for a general perspective on how human intuition works, it's useful to get in the mindset of the hunter-gatherer tribe, because the current way that we live with the internet and computer chairs and all this advanced technology and cars and stuff is very different from the format that we've lived for the majority of the species' existence. So a lot of the shortcuts that we take are going to be the most advantageous in that context, as opposed to in the classroom education context. Like hunter gatherers that are out in the jungle, they're not like sitting down in a math course. If sitting down in a math course and like being in a circle would have helped us stave off predators and get more resources back then it would have been successful. But this is one of the things that has been gaining the most momentum after we figured out food. So we invented agriculture, which meant people could specialize. You didn't have to have every single person as a hunter or a gatherer. You could have a scribe and a politician, mathematician, stuff like this. So when you see these polymath people, they wouldn't have had the time to do this if they had to go chase stuff down on the savannah. So it's a really key kind of turning point, and really useful, I think, for understanding not just what human intuition is, but what environment shaped it.
Absolutely. Yeah, totally agree. One question I have maybe for the audience, though, we'll see how this goes also for you, is like what kinds of topics would be really interesting for the future? I know one that we had in mind was maybe to start talking about logical statements and starting to train this mathematical way of thinking. But I'm curious what specific things people might be interested in or want to learn about.
I think for me personally, that one would be the most translatable for the audience and the most immediately applicable, because some of the really common flaws I see in conversation is people will start from a point where people aren't in agreement, like the premise is not clearly agreed upon, and then they'll take a bunch of shortcuts and also maybe use some different debate tactics that can make the audience think that they're winning the debate when they're really not. So that could be one. I think from your area of expertise as a mathematician rather than as a philosopher or linguist or whatever, it would be interesting to see kind of the background of how a lot of that knowledge and wisdom was built up.
Yeah, I think that I definitely concur. I think we've also mentioned that, like, you have some poker expertise. You also play some games online that involve chance. We could try to analyze some of the games that you've played in the past and try to come up with some interesting examples to see how probability works in the field, so to speak.
Yeah, it might be interesting too for finding some like StarCraft themed discussion. I think we would need to think about what data we could pull for that, but there are a lot of areas where you could potentially find success, kind of what AlphaStar does by performing a whole bunch of different trials in a very like high speed environment where they can train faster than any human, and basically finding some best fit path through the ladder with each of the three races, and how that is shaped based on your experience. Sometimes I'll vaguely think about this of like I face two base all-ins from Protoss about half the time, and then the other half of the time they end up taking a third base. So I'm kind of gauging my strategy around a set of expectations based on my previous experience, which is probability that is a result of human behavior. Human behavior is really awkward to quantify as well, though.
I see. Probability models for like human behavior, sure. Um, yeah, and there's definitely things we could also do that are non-probabilistic for StarCraft, like modeling. I mean, these are very simple, but you can model how like income grows and like making a decision between building a drone or how to use your larva or what buildings to build and how that affects your production over time. These are definitely things we could discuss.
Oh, well, there's one aspect of StarCraft that I've asked for at BlizzCon. You know how it has a kill counter on a Zergling or a Ultralisk or whatever. When it kills stuff, there's a little counter. I wanted to see on the workers how much resource they've mined over the course of the game, because I think that's something that would blow a lot of people's mind, just to see the numbers for the value of the drone that you had at the start of the game. If it's been mining for a 20-minute game, how much resource has it mined? And then you could
Sure.
do some equivalencies if this was like 15 Ultralisk worth of value or something.
Yeah, a lot of interesting things there, and we can look at the plots that you see at the end of the game and the rate of mining and like how much minerals there is and what did you spend it on and when did you spend it and what how is there a way to improve your outcomes. I think there's definitely a lot of decisions someone makes in their build order and maybe later in the game that we could try to put some kind of mathematical model on, or maybe some simple analysis to illustrate the concepts.
I have such a really common mistake that I make when I won't think about the game state mathematically. Say I get a worker lead, so I have 80 workers against my opponent's 65, and I'll feel like I'm in a really good spot, and in a way I am, but I'll choose to attack, which goes against what my advantage is because I'm collecting more resource. So if you were to graph the resource over time, I'm going to have so many more options and so much more power than my opponent. But in the immediate term, that advantage hasn't really come to fruition yet. It's an advantage that mounts the longer that I wait. So that's one of those things where patience is the virtue, and being able to flesh out the math, I think, would help to remind me of that at least.
Like understanding where your power spikes are, sort
Yeah.
of like, yeah, like so you've hit some kind of timing and that's the time you want to attack.
Yeah, power spikes
Yeah.
would be really interesting to investigate for StarCraft as well. I think I have a vague sense of what some of them are. Like I've described, Protoss has a 2 base power spike because of Chrono Boost, and then Terran gets a small power spike every time they hit a mule, and then Zerg gets
Well,
theirs when they have their bases injected.
yeah, yeah, certainly. Um, the other thing I've just sometimes thought about casually is like I probably could give a pretty good mathematically formal definition for what meta means, because it seems like a lot of people say the word meta and they all just say it like sort of casually without any type of real definition. And like I think we could make it formal and precise. That's not really going to help anyone's game. I just thought of it as an interesting sort of pedantic way of looking at language and mathematics.
No, I think it would be good actually to do some discussion on what the different terms are that people throw around in StarCraft, and what if we did like set them to be a certain thing, what would they be? Because meta, from my perspective, is the full set of what all the human players are doing in the game right now. But what people use it for sometimes, they say meta as in what is popular and played at the highest level. Like you see it in tournament games, and it is, quote, standard practice for them to do those things. So they'll use meta for that sense. And then another
Yeah.
really fun common question is what defines a cheese or an all in? That's one that people have debated since StarCraft 1. So that might be fun
Sure.
to just kind of shoot the shit about.
Yeah, I think the all-in one I think also is sometimes stated in anger.
Yeah.
Like I lost and this person just knows how to all in and that's why they won. They're not better than me. For the meta one, yeah, I think what you're saying is very close to what I would have said, that there's this list of possible strategies, but on top of it, there's also potentially a distribution of what strategies are being played at your level. And that would be like maybe the meta for your MMR.
Mm-hmm.
I definitely, so I've heard some questions in chat. There's one about discussing medians and averages and standard deviations, the general, like, simple concepts from statistics and statistical analysis. I think that would be very useful for various reasons. One, because the number of people throwing out random statistics, especially in this election season, being able to better understand that, because a lot of the times when people speak using math on contemporary issues, they speak in statistics, and trying to understand what statistics means and how is it possible that we can infer things using data, and this notion of maybe the Bayesian way of looking at statistics versus the frequentist way of looking at statistics. I think there's a lot of interesting philosophical and practical discussions there that could help people.
Yep, for sure.
Another thing we could do if people are interested, I'm not sure what percentage of your students are deciding on like what they want to do in the university or in school, but we could give some guidance on that. Like maybe you could talk about the classes that really you enjoyed and helped change your mind, because I think finding classes that really motivate you is very important. And I can give some guidance on, like, if you wanted to get a certain outcome, maybe you want to go to grad school, maybe you want to work in data science, or maybe you want to work in finance. Like, what are the classes you might want to choose in math? Maybe even if you're not a math major, what are the classes that maybe give you the most bang for their buck? That might be something people are interested in.
Yeah, I didn't, from my personal perspective, I didn't really, I think, get super excited by math and fall in love with it until I got into the calculus courses. Before then, a lot of it did seem very like basic, just plug it in kind of stuff. There's a little bit of creativity to it, but not a whole bunch. And I think many people don't really get to the courses that are really exciting. Of course, it's not for everyone. We're not saying that everyone needs to make math their new best friend, but sometimes you just haven't really found the type of math that is really fun and exciting for you, because some of it is very visual in that sense too, like geometry. There's a friend of mine who I went to university with who kept with math, and he's been doing topology and stuff with. That's really mind-blowing.
Oh yeah, yeah. There's lots of yes, absolutely. Yeah, I've done a bunch of topology, and it's yeah, mind blowing is a good word. Um, Yeah, I think that experience you described is common. That someone some point in their life finds this like one either special book or special class, and maybe it was a good time for them. It was a good teacher, or maybe it was just the right perfect storm of good events that they just fall in love with one topic. And in exploring that one topic is really like sort of their gateway to becoming just enamored with all of math. I remember personally, I had taken calculus, and just a standard calculus course, and I was helping some friends, like kind of like a homework and stuff, with their homework and stuff. And I realized after a little while that even though I'd taken a bunch of calculus classes and I thought I did pretty well in them, like I had no idea why anything was true. So if they even poked at all at the solutions I was helping them get, just the slightest bit of depth there, I wouldn't be able to help them at all. And I felt really inadequate in that respect. And then I was like, there must be something deeper here. I want to know the real answers. I want to explore. And so I looked online and looked for like the right book to satisfy this need. And I found this one book by this author, Thomas Apostle, on calculus. And it was sort of my first math book I really loved. And it was essentially calculus and why it's true. And that was sort of my gateway.
Yeah, it's fun too, like finding why it's awesome. Like there's the value of it in the practical sense, but then there's the cool factor of hyping people up. Carl Sagan was a big influence for me, especially in how he emphasized that through his Cosmos book and then TV series, was not just telling stuff like it is, but focusing on how stuff is amazing and mysterious, and there's a lot of stuff to discover. And firing up the young generation is a really, really important part of us progressing technologically as a civilization. It's not just about what the mathematicians are doing right now, it's also about uh, being able to pitch to people like math is really awesome. And if you went for this, there's a lot of amazing things that you can contribute to society. It is more abstract compared to certain other fields that have like a more immediate physical payoff. Like civil engineer, you design and build a bridge and people drive over the bridge. You get that immediate feedback of what has been done with that. Whereas something like probability theory has a ton of applications. It's not one that whenever they discovered it, it's like, oh, you've saved the world with this probability theory. Most people probably didn't even know what was going on at the time, and that
Yeah, who are these weird mathematicians meeting in France in the 1900s?
yeah, exactly. So it is more indirect in its contribution, at least in the payoff of that contribution, but it's really massive and broad based. Mathematics is very beautiful, and in a way, it's kind of more pure than a lot of applied stuff because it's not as messy. You get to create that really clean scaffolding so that you can think about reality as opposed to needing to go with all the bends and twists and remainders and decimal points and stuff. Ugh, nobody wants to do that.
Yeah, I mean, the beginning of a lot of math is you take some physical phenomena maybe that you're interested in or some other kind of phenomenon, and then you create a model for it. And from that point on, you're sailing in math land where everything is pure and perfect. And you let the model sort of be your interface between the messiness of reality. And the model isn't perfect. It's not correct. It's wrong, but it still makes useful predictions on the world. And so that's sort of the general process of mathematical modeling.
Someone asked, do I think there are limitations on some people for understanding math? Like some people grasp it better, or is it a question of time needed? So that's kind of almost a general question of what talent is. Certain people are talented with math where they don't have to look at the same problem for as long as other people, but everyone has to study and everyone has to experience and do problems and learn. Talent is basically just a factor on your learning rate for the time that you spend. So, say you have a class like you take linear algebra in university. To get a 95, you might have a couple kids in the class who just need to stay awake and they go to the test and they get a 95. You might have some people who need to do the homework and then do some problems. And then you might have some people who need to get a tutor to help them think about stuff. So basically, it's about finding what works for you for learning math. And it's okay if you need to ask someone for help. Asking people for help is a really good life skill as well. Some people have that sense of ego where, if I ask someone a question, that means that I'm not the smartest person in the room. Now, the smartest person in the room is usually a person who asks questions pretty frequently because they want their understanding to be clear and complete.
Yeah, absolutely. I think some people, when they ask that question, like limits on understanding, they have this model where they're like, okay, some people can do math, and then maybe I'm worried that like I'm just never gonna quote unquote get it, and that's almost always wrong. There's not like there's this cap of math skills, and if you don't like in some like pure way exceed that cap, then you're just like you shouldn't just stay away from math. It's not for you, and that's almost always wrong. But yeah, it does take work. It's true that some people, either from their background or just naturally, seem to get certain concepts quicker than others. But I mean, that's true for all. I mean, for example, there's some people for which the topics of calculus called analysis in mathematics are very easy, but they don't gravitate as much toward algebra. And there's people for who algebra is quite natural and beautiful and amazing, and they don't like analysis as much. And both of those types of people exist. Another thing that can sometimes be discouraging is that someone, let's say, goes to read a book, a fiction book, and they're like, oh, yeah, it's really interesting. I read about 30 pages yesterday. Or on contrast, if you try to read a math book, you usually measured in how many hours did that page take? Or maybe it's been a day and I'm still thinking about that page. So you have different expectations because some of the math stuff really does need deep thinking, and you really have to change the way your mind works. So sometimes people's expectation of how much time it takes needs to be readjusted. Also, often in school, because of all the other responsibilities you have, maybe you're playing some video games, you don't always have the amount of time you need to work on something. And you really need to put yourself in the right mental state and have the right amount of time to learn something. And sometimes school doesn't always give you that.
Yep. There's a good comment in the chat here. It depends on the teacher as well. Most math people are really smart but aren't able to convey it. Others can. That kind of connects with what my role is in the StarCraft scene. I'm not anywhere close to as good as Cyril or Dark, but being able to describe the situations in English to people who are non-experts is a really important niche to fill for any math, science, discipline, art. If you have a skill and you want to be able to convey that, it takes language and connection with the people you're trying to teach, where you're meeting them where they are and setting them in the right direction rather than just speaking in your language about how to do stuff. I know that a lot of times, if you've already figured out something on a very deep level to the point that it's intuitive for you, a lot of the wrong answers are no longer a part of your thoughts. It's not like a chess grandmaster sees all the moves in front of them. Usually they only see the decent to excellent moves. And the bad moves, they don't even process anymore. Whereas a new player doesn't have any of that intuition at all. And they see the full set of moves and they have no idea what's good or bad. So I think it's really fun bringing you on too, because we're speaking to people on Twitch. This isn't a university course. You didn't have to have any requisites to be here. I know there are some people in the chat who have extensive math background, and that's really awesome. And then some people who maybe had bad experiences with math, and you're like, I don't know why I'm still in this stream. But it's good to have you here.
Yeah, hopefully if you had a bad experience, we can help rectify that. I think it's also amazing with your StarCraft that you're able to not only give very clear explanations, but do it while you're playing, which sounds like crazy to me. It's almost like, I can't do this myself, but like people who can like sing very well while playing an instrument, that those two skills simultaneously is pretty amazing.
Yeah, it's about a 200 to 300 MMR hit to the
Wow.
like full skill to be talking. It depends a little bit on my performance. If I'm having a really good day, physically, I think the impact is less. But if I'm having a tough day, then it's pretty heavy to carry both of those at the same time. But for the audience, usually they care more about the engagement more so than the maximum performance from me.
Sure. Yeah. Yeah. They're here for you.
For the hilarious story of the ladder games.
So I think there's tons of topics that we could discuss, and yeah, everyone's questions have been very good. There's also lots of places, other resources other than us. Actually, there's other resources other than the stream where you can learn math online. Some great ones, depending on your level. There's MIT has a whole site of all their math materials and all their other materials free called OpenCourseWare. There's sites like Khan Academy. I mean, Wikipedia is a great resource too. It's amazing the depth of knowledge on Wikipedia. Coursera offers a ton of courses. YouTube has tons of people giving math lectures at all levels and some really good teachers. In fact, there's two YouTubers who have really beautiful graphics in what they're doing. I think one of them is 3 Blue, 1 Brown. There's also Robert Greist on YouTube. Both of them have made some beautiful visualizations, which really can help. I mean, sometimes having really good examples is good in understanding anything, especially in mathematics. So there's I don't have a comprehensive resource of list of all the good places to learn math online, but there's many, and I've seen a few even mentioned in chat already that I'm going to check out.
Hell yeah.
So maybe we should speak for a moment. So we had some ideas for the structure going forward for the podcast, and we thought, credit to Neuro, that giving some historical context might help bring some of these mathematical topics to light and show that math doesn't just come fully baked. Actually, it's like hundreds of years of different people working on it. So the math, which you learn so quickly in maybe a few weeks, actually took decades and centuries to actually come up with. So these concepts also have historical meaning. Like they came up at certain times, contemporary with other discoveries in maybe physics, astronomy. But we also planned on doing some quote unquote actual math. So starting to build those logical way of thinking, starting to look at maybe we could together try to solve the problems that Gambeau proposed to Fermat and Pascal, or the original problems that Cardano was looking at. Or we could look at the original axioms of how probability became a formal theory and understand the connections with area, or understand what is statistics and what does it mean at a formal level. So yeah, we even have some stuff prepared, which maybe next podcast or whenever, where we could start talking about how to make precise logical statements. And I think that could be really interesting. And maybe we'll have some moment. Well, this is still something I'm thinking about, but we could have moments where the chat has to answer a question, and we'll have a bunch of interactivity. But I'm not sure how well that will work, the timing or not. So I think there's a very interesting sort of arena of trying to present math in an interesting, interactive way to a Twitch chat, that'll also become part of a podcast. And I think exploring that space and doing it well, there's really a lot of opportunity to do something amazing.
Yeah, we're blazing trails right now. We did get a raid from Rocket Sage, who is a part of the Knowledge Foundation, which is kind of a educational focused group of people who stream on Twitch. She does geology stuff. There are quite a few other people in TKF who have educational content they do on Twitch. I'm not consistently doing educational content unless you count the StarCraft stuff, but we're doing the philosophy with Eche Fatum. We do world discussion with Agent Smith on Sundays, and then this is the first ever discussion with Brett on math. So yeah, it's a really awesome thing having you on here. I was thinking with your discussion there about the context, Isaac Newton's quote, "If I have seen far, it is because I stood on the shoulders of giants." So all those slides that we went through pretty quick there, those are the giants who figured shit out and did the hard work. They're writing letters to each other around the world trying to figure out how to solve one tricky problem. And then once that tricky problem gets solved, then all of mathematics can build upon that. So we take a lot of our technology and things for granted, I think, and the painstaking effort that human beings applied over the past thousands of years to make that stuff possible for us. Thank you, mathematicians. Now we
Well
all have
put.
phones.
Yes, physicists, mathematicians, and many others. Yeah, and now we have cell phones. That's the answer. The end.
We've got smartphones. We're done. All right.
That was it. We did it. We math done. Yeah, it's yeah, and also the for those who have maybe indicated this in the chat, the logical mathematics that we want to present will have no prerequisites. It will be, you basically just have to come and be interested and want to participate. And no hidden prerequisites either. Like really none. You just have to want to think about stuff. And it'll tie in, I think, well also maybe with your philosophy stuff, because logic and philosophy and thinking precisely, I mean, they go hand in hand.
Well, unless you want to do bad philosophy.
Always an option.
Well, awesome. Was this about the rounding off of the discussion that you had? There was a question. What would you recommend to get better at counting? Say I have something in which it can have a max of 4 lines connected to it. How would you go about counting the different possibilities that it could have, assuming given n lines?
Can have a max. I have to be honest. I don't exactly understand what's being asked. I mean, and maybe I could stay on the chat afterward and maybe offline get a more precise description and try to think that problem out with that viewer. But yeah, at the moment, I don't. It sounds like a problem, so there's a field of math that's totally devoted to like counting things. It's called combinatorics, and combinatorics is also notorious for having problems that are very simple to state and very hard to do. But I want to better understand that particular question. So maybe we'll do that. I could do that offline with that viewer.
Let's do let's make a math text channel in the Discord, because I have a philosophy one and a politics one now. So that could be a cool place where people can pose different kinds of questions, figure out what's what, and also we can discuss leading up to the next session that we have together, what people want to have spoken about. I know we have quite a few mathematics aficionados in the stream.
Yeah. The material we had planned for which we don't have time for now. We prepared pretty sure we weren't going to get to it. It's just going to be like simple logical statements, and we actually had this chessboard involved, and I think it'll be an interesting way to start. And then I think a lot of the suggestions being made in chat could definitely follow from there. I think it sounds really fun.
Sweet. Well, did you have any final thoughts? This will be going on YouTube, everyone. And we may be able to get this into a podcast format as well. The Zencaster stuff wasn't working out for us for whatever reason. We should be able
We can
to
try to work on that to get that to work next time.
Yeah. Your audio sounds quite good to me. I'm glad that you got the microphone upgrade. Very much appreciate that. You've been...
Oh, I'm glad. Yeah,
clear
I wanted to make
crisp.
sure it sounded good.
Yeah. Listenability is very important.
Yeah. So I guess we'll offline discuss what we want to do about the next one, and I'm excited. I think this is the start of something that could be very interesting, and hopefully very informative and fun to watch.
Of an epic adventure on the field
Yes,
of maths.
This is just the beginning, and we'll remember this first one and be like, oh, you remember when we still had that format? So glad we switched off of that.
Yeah, we're going to have
look back.
3D holographics coming up soon, ladies and gentlemen. Popping out of your computer screen. Get ready. Get your 3D glasses. Oh, that would be sick.
Yes.
Thank you very much, Brett, for coming on. It's been awesome having you. I'm glad that we
You're
got
welcome,
this
and thank
going.
you for having me.
And thank you, chat, for your insight and your questions and your interest. Appreciate you being here. Let us then ring the gong, and we shall conclude this first episode on maths. Thank you, everyone. GG.
GG indeed.
Okay, I will head up now. Later,
Sure.
Brett.
See ya.
Nice.